Good afternoon. My name is Carla Palma and I'm head of the Chemistry and Marine Pollution Division at Hydrographic Institute. My following presentation covers the measurement uncertainty evaluation based on in-house validation data applied for heavy metals in sediment analysis. One of the activities of our division is the characterization of sediments to be dredged in compliance of Portuguese legislation. This characterization should be carried out in terms of metals and organic compounds, and at the end, sediments are classified from class 1 to class 5 according to the concentrations of the different parameters. The sediments that are from class 1 has no restriction and can be deposited anywhere. The sediments that are from class 5 should ideally not be dredged or, if imperative, should have a prior treatment. It is essential that the results reported in this type of analysis are adequate and obtained through validated procedure and with known uncertainties. The measurement procedure used in Hydrographic Institute for metal determination follows the guidelines of OSPA or the guidelines of Environmental Protection Agency, and the procedure starts with sample digestion, preparation of calibration standards, quantification of the elements in acid extract performed by atomic spectroscopy. The measurement trueness can be assessed from results of the participation in international proficiency tests. The reference value of proficiency test samples is the consensus mean of the results from participants that proved to be adequate to assess the performance of laboratories involved in environmental monitoring. In this graphic, you can see the results of these scores for copper between 2002 and 2022, and the results of this score have a satisfactory performance, as you can see. The analysis of trace levels of analytes in complex matrices are affected by matrix effects due to different characteristics of the sediment, like mineralogy, grain size, characteristics of metals, pH, organic matter, oxidation reduction potential, and are responsible for larger deviation between results. The validation of the measurement procedure produces measurement results in an adequate analytical range with a measurement uncertainty smaller than the maximum value admissible. It is necessary to take the variability of matrix effects into account. The top-down evaluation based on in-house data is based in information collected during validation of the measurement procedure, involves quantifying and combining the uncertainty due to measurement precision and trueness, and quantify the measurement uncertainty that includes the variability of matrix effects. In the top-down evaluation of the uncertainty, there are 4 steps: the measurement definition, the identification of uncertainty components, the quantification of uncertainty components, and the components combination and subsequent expansion. The top-down evaluation involves quantifying three uncertainty components: precision and trueness, and additional components not quantified in the two other components. For the uncertainty components quantification, the measurement precision is quantified by the intermediate precision standard deviation. The measurement trueness component is quantified from the analysis of reference materials, such as proficiency test samples, are obtained by the mean recovery standard uncertainty and comparison with the ideal recovery. And others are components that are not considered in the other two components. For example, the sampling uncertainty. The components are combined: precision, trueness, and additional uncertainty using the law of propagation of uncertainty. Whenever the uncertainty components are associated or expected to be associated with a large number of degrees of freedom, the standard uncertainty can be expanded to around 95 or 99% confidence level by using a coverage factor of 2 or 3 respectively. The intermediate precision component is quantified by the absolute or relative intermediate precision in two intervals. The variation between the absolute precision and the measured quantity value is constant below 2 times the limit of quantification, because the relative precision of the measurement decreases in an abrupt way in this first interval. Above the 2 times, the relative precision becomes approximately constant. If instrumental precision is estimated at more additional quantity levels, the respective intermediate precision, relative standard deviation, can be used to improve the precision model. And the model is: consider the intermediate precision in absolute value below 2 times the limit of quantification, and consider the intermediate relative precision above 2 times the limit of quantification. The trueness uncertainty is assessed from results of the analysis of reference materials, what means materials with a reference value. Proficiency test items with adequate reference value are fit for this assessment if several results from the analysis of reference materials are available. In this way, it is possible to understand the variation of the recovery with the quantity. The standard uncertainty from measurement precision can be estimated by pooling standard deviation of measurement obtained under intermediate precision condition in the first interval. The relative standard uncertainty from measurement precision is obtained from the pooled relative standard deviation of measurement obtained under intermediate precision condition for the second interval, interval 2. The trueness uncertainty is the standard uncertainty from measurement trueness and is estimated from the recovery observed from the analysis of different samples from proficiency tests. And the relative standard uncertainty is estimated by dividing the standard uncertainty by mean recovery. The mean recovery is subsequently compared with the ideal 100% recovery value to decide if the measurement values should be correct for the observed recovery. The mean recovery is meteorological equivalent to 100% when this second condition is valid. The uncertainty components are combined and subsequent expansion. The first equation from interval 1 combines the standard uncertainty from measurement precision and the standard uncertainty from measurement trueness. The second equation from interval 2 combines relative standard uncertainty from measurement precision and the relative standard uncertainty from trueness. For the two equations, the expansion is done with a coverage factor of 2. In this work, it was studied the determination of the total mass fraction of different elements using marine sediment, and the procedure developed by OSPAR for chromium, copper, lithium, manganese, and zinc, and the Environmental Protection Agency standard for nickel and lead. In figures, we can see the variation of analytic recovery with the mass fraction observed in proficiency test for the analysis of different parameters in marine sediments. It can be observed that no strong variation of recovery value with measurement value is observed. This table presents the measurement performance data and summarizes the validation of the uncertainty models. Here we can see the different elements, the limit of quantification for each other, the standard uncertainty from measurement precision and from measurement trueness, the relative standard uncertainty from measurement precision and from measurement trueness for the two intervals, the recovery and if it is necessary to correct the recovery, and the combined uncertainty and the expanded uncertainty for the two intervals. The adequacy of the developed model of the measurement uncertainty was assessed from the analysis of materials from proficiency test, independent of the ones used in the evaluation of the measurement uncertainty. All estimated and reference values are meteorologically compatible for a confidence level of approximately 99%. Since all estimated ranges are smaller than the expanded uncertainty of the range using a coverage factor of 3. The uncertainty model were 100% successful when applied to the analysis of 15 to 20 samples from proficiency test, independent from those considered in the evaluation of the measurement uncertainty. The estimated relative expanded uncertainty ranged from 12 to 25% and are fit for the monitoring of contaminants of marine sediments, considering the criteria for assessing the performance of participants in the quasi-MEM proficiency test. A tolerance of 30% was considered in the comparison between the calculated and target standard uncertainty. The developed methodology for the top-down assessment of matrix effects and for the evaluation of the measurement uncertainty, including the impact of matrix variability in measurements performance, was successfully applied to the determination of different elements in marine sediment. sediments. Two models of measurement uncertainty was developed for the determination of each parameter. The estimated relative expanded uncertainty are lower than the target uncertainty inferred from how z-score are calculated in quasi-mem proficiency test. Thank you for your attention.